So we are going to do some bilateral Laplace transform right now. This will make our concept more clear as we do proceed into the math. Alright, so this is our signal, and as it is written, it's called causal signal. We're gonna do bilateral Laplace transform of causal signals, and the most famous causal signal on whole of Laplace transformation is e to the power minus at ut. It occurs on transients, it occurs everywhere on circuits. Alright, and we want to find out how its Laplace transformation is. But before I move on, I want to say a few things about causal, non-causal and anti-causal. Causal and anti-causal are very straightforward. Causal means it will have its value after t equals to 0, and before t equals to 0 is going to be 0. Anti-causal is just the opposite. It is going to have its value before t is equals to 0, and after t is equals to 0 is going to be all 0. And non-causal is basically just going to be the summation of these two signals. It's going to have a causal part plus and a non-causal part, so it's going to have value before t equals to 0 and after t equals to 0. So that's all for three types of signals, and we're going to see Laplace transformation of all those signals right now. So right now let's convert it to the Laplace domain. Alright, so xb of s according to our formula is going to be minus infinity to infinity e to the power minus at ut e to the power minus st dt. That's definition, right? Now this ut is going to be 0 before time equals to 0, so we can change our integration limit to 0 to infinity and remove u of t, so that is going to be minus e to the power s plus a t dt, and this integral, if we evaluate it, is going to be minus 1 by s plus a e to the power minus s plus at from 0 to infinity. Now when s plus a real part of s, I should have been more accurate, when real part of s plus a is greater than 0, this portion is positive, and when I put infinity on here, it's going to be e to the power minus infinity, which will become 0, and the integral will converge, right? Otherwise the integral will not converge if this is negative, and it will become e to the power plus infinity, because minus minus will cancel out, and that's not what we want. So our reason of convergence is obviously going to be real part of s plus a is greater than 0, or to be more specified, real part of s become greater than minus a. Alright, so let's put on in our region of convergence, if we put infinity, then it's going to be e to the power minus infinity minus e to the power 0. So this is going to cancel out, and its value is simply 1. Minus minus will again cancel out, so it's going to be 1 by s plus a. So it's our Laplace transformation. The exponential factor has become on here, and try to notice that when s equals to minus a, the Laplace transformation value is infinity, and this is called a pole of our signal. All right. And what's the reason of convergence really? Let's guess that a is a positive value. All right, so a is here, then minus a is going to be here, then our region of convergence is going to be all the right side from minus a. So there is really a lower limit, but there is no higher limit of how much real part of s could be, and you have to be careful about that. We will see that how it gets used later on. So for causal signal, the ROC is on the right hand side of our pole, and it can be as big as it can. For causal signal, there is a lower limit, but there is no higher limit. All right, so we're going to do Laplace transformation of exactly opposite signal, anti-causal signal right now, and it's given on here. So if we do our Laplace transformation, then according to our analysis function, is going to be minus e to the power minus at u of minus t e to the power minus st dot dt. If I take the minus outside, and as u of minus t has value of 1 before 0, so I can change the limit to minus infinity to 0 and remove u of minus t, and then it's going to be minus s plus a t Now let's try to do the integral. Minus minus is again going to cancel out. 1 by s plus a e to the power minus s plus a t. Now 0 to minus infinity. If I try to put on the value, then it's going to be 1 minus e to the power minus s plus a, minus minus again cancels out, times infinity. Now if s plus a, that means real part of s plus a, because other j omega is just a phase. If real part of s plus a is greater than 0, then it will become unbounded. We don't want that. But if real part of s plus a is less than 0, then it will be e to the power minus infinity, and that will become 0, and we will have a finite integral value of 1 by s plus a. So our region of convergence is real part of s is less than minus a. If we try to plot that on our s domain plane, this is sigma, this is j omega. So let this be minus a. Then the ROC is simply on the left hand side, so there is going to be an upper limit, but there is no lower limit. Alright, so for anticausal signal, the ROC is always on the left hand side, and for causal signal it's always on the right hand side. Try to grasp that concept. Now there's one more thing, one more really short notes we can take from here on. See, on here on the ROC there was j omega plane. Therefore if we take a, if we assume that a is negative, then our j omega is not on our ROC plane. When we can also come to the decision, when will Fourier transform exist? You see, Fourier transform, as I explained in my past video, Fourier transform is the line j omega in the S domain. So Fourier transform will exist if and only if j omega line is in ROC. So it's a good idea, and it's good to know, useful to know, and handy to know sometimes. Alright, now we are going to see a non-causal signal. That means it's going to have a causal part and it's going to have an anti-causal part. Remember, it's not always going to be bisected like this. I can give you a signal like this and like this, and you might have to take them in the form of elementary signals. So be careful about that. Right now let's move on to the mathematics. So consider it as x1 of t and consider it as x2 of t. Alright, then x1 of s is going to be 1 by s plus 5, and 2 is going to hold on because integral in the constant really come out of integration, and from our past example we know at e to the power minus at is 1 by s plus a, and our region of convergence is going to be real part of s is greater than minus 5. Alright, now for x2 of s, it's going to be 1 by s plus 4. But remember, for anticausal signal there is a minus e to the power minus at e of minus t has a Laplace transformation of 1 by s plus a. So e to the power minus at e of minus t will have a Laplace transformation of minus 1 by s plus a. So it's going to be minus 1 by s plus 4, and our region of convergence is going to be real part of s is less than minus 4. If we try to combine the two ROC, then we will get the ultimate ROC of our non-causal signal. So our ultimate ROC is minus 4, real part of s is greater than minus 4, is greater than minus 5, and less than minus 4. So it is our ultimate ROC. Remember, whenever you do any sort of Laplace transformation, you always have to mention your ROC. Now in this for this example, the ROC is between minus 4 and minus 5, and there is no j omega line here. So for this signal there is no Fourier transformation possible. Alright, so right now we are going to do inverse Laplace transformation, one easy inverse Laplace transformation. We'll go to inverse Laplace transformation more usually later on, but let's just do it right now. So all the things that we have learned till now were really something divided by s plus what, something divided by s plus x. So it begs for partial fractions, right? we, there will be a whole lecture on partial fractions, but let's just do it right now abruptly as far as our knowledge goes. If we try to fraction if we try to make it into the multiplication factors, then it's going to be s plus 2 s plus 1, that's factorized. Now you know how to take it into partial fractions. There is a shortcut. I'm going to use the shortcut s plus 2, so that means if the pole is minus 2, so just put the value on the denominator, minus 2 plus 1 and minus 2 plus 4, and then s plus 1, so pole is minus 1, so minus 1 plus 2, just put the value on the other factors, and minus 1 plus 4. So ultimately what do we get? Ultimately we get 3 by s plus 1 minus 2 by s plus 2. And right now comes a point which we have to first understand before going to time domain. First partial fractions, then you will have to see your ROC, because remember that when you want to move from time domain to Laplace domain, your direction is fixed. You are going to go into one Laplace answer only. But try to understand that 1 by s plus a, its time domain function could be very easily e to the power minus at u of t or minus e to the power minus at u of minus t. So this inverse Laplace transformation is really not one-to-one. It will have to depend on ROC. So first very easy thing to do is to plot your ROC really. So it's between minus 2 and minus 1. Alright. Now let's guess that minus 1, this pole, is an causal pole. If it was a causal pole, then the ROC would be right hand side of it, so there is no way that is going to happen. That's not our given ROC. If it is an anticausal pole, then the ROC is going to be the left hand side of it, and then there will be some chance. So it's obviously have to be an anticausal pole. So the Laplace transformation is going to be minus 3 of e to the power minus t u of minus t, and then minus 2. Now for minus 2, we see that the ROC is on the right hand side of it, so it's going to be a causal pole, and the anticausal and causal's intersection is our ultimate ROC, right? So it's going to be minus twice e to the power minus 2t u of t. So the concept is that once the ROC is given, you can come back to your time domain functions, but without ROC it's not uniquely defined. Inverse Laplace transformation is never uniquely defined without ROC. Alright, so that's what I wanted to share in this lecture, some of the bilateral Laplace transformation, and in the next lecture I will show some of the unilateral Laplace transformation of some familiar signals. Thank you.